Practical Applications of BPT and its Converse. Welcome, everyone. Before we dive into today's lesson, let's take a moment to reflect on what we have already covered. In our previous sessions, we successfully established the fundamental principles of the Basic Proportionality Theorem, commonly known as BPT, as well as its converse. Now, it is important to remember that while these theorems provide us with the essential theoretical foundation, their true mathematical value isn't just in memorizing the rules. It lies in how we strategically apply them to solve much more complex and intricate geometric problems. In this tutorial, we are going to move beyond simple definitions. We will focus on three primary practical applications. First, learning how to manipulate ratios to find new proportions. Second, analyzing the properties of trapeziums. And third, using these tools to identify specific types of triangles. Let's get started. 1. Extended ratios, from segments to whole sides. As you know, the standard BPT tells us that if the line segment DI is parallel to the base BC in triangle ABC, then the ratio of the segments is equal. Specifically, the ratio of AD to DB equals the ratio of I to EC. This is a part-to-part ratio. However, in many complex geometry problems, like the ones we will see later in our discussion on trapeziums, we aren't just looking for the ratio of the small segments. We often need to find the ratio of a small segment to the entire side of the triangle. The core concept here is that we can mathematically manipulate the BPT ratio to prove what we call the segment-to-whole ratio, which is AD over AB equals I over AC. Let me walk you through the step-by-step derivation so you can see how this works algebraically. First, we start with our standard BPT assumption. Assume DA is parallel to BC. This gives us our starting equation, AD over DB equals I over EC. Second, to make the algebra much easier to handle, we are going to invert the ratios. We'll take the reciprocal of both sides, which gives us DB over AD equals EC over I. Third, we use a very useful algebraic trick. We add unity, or simply the number 1, to both sides of the equation. So, dB over AD plus 1 equals EC over I plus 1. Fourth, to combine these terms, we need to find a common denominator. We can express the number 1 as AD over AD on the left side and as I over I on the right side. This transforms our equation into dB plus AD, all over AD, equals EC plus I, all over I. Fifth, we simplify the numerators. If you look at the triangle, you'll see that dB plus AD is simply the length of the entire side, AB. Similarly, EC plus I is the entire side, AC. So, our equation now reads, AB over AD equals AC over I. Finally, we perform one last inversion. By taking the reciprocal once more, we arrive at our final extended ratio, AD over AB equals I over AC. Now that we've established the theoretical foundation of the Basic Proportionality Theorem in our introduction, let's move on to our first practical application, moving from extended ratios to whole sides. Now we have a powerful tool to relate small segments to the full sides of a triangle, which will be incredibly useful when we tackle the properties of trapeziums in the next slide. 2. Trapezium properties. First, let's refresh our definition. A trapezium is simply a quadrilateral that has at least one pair of parallel sides. Because of this parallel structure, the Basic Proportionality Theorem, or BPT, becomes an essential tool for proving various properties within these shapes. To help you visualize why this matters, think about a real-world analogy. Imagine a structural support beam in a bridge shaped like a trapezium. If an engineer installs a crossbrace that is parallel to both the top and bottom bases, that brace will divide the side supports in exactly the same proportion. This isn't just math, it's structural stability. Now let's look at a formal problem. Suppose we have a trapezium ABCD where the side AB is parallel to the side DC. We draw a line, EF, which is also parallel to AB and by extension parallel to DC. Our goal is to prove that the ratio of I to ED is equal to the ratio of BF to FC. At first glance, BPT is hard to apply directly to a trapezium because BPT is a theorem for triangles, not quadrilaterals. So, we need a clever strategy. Step 1. Construction. We cannot work with the trapezium as a single block, so let's draw a diagonal AC. Let's also note that our line, EF, intersects this diagonal at a point we'll call G. By doing this, we've split our trapezium into two triangles. Step 2. Let's analyze the first triangle, triangle ADC. Because the line segment EG is parallel to the base DC, we can apply the Basic Proportionality Theorem here. This gives us our first equation. The ratio of I to ED is equal to the ratio of AG to GC. Let's label this as equation 1. Step 3. Now, let's look at the second triangle, triangle ABC. In this triangle, the segment GF is parallel to the side OB. Applying BPT again, we find that the ratio of AG to GC is equal to the ratio of BF to FC. We'll call this equation 2. Step 4. Now, look at what we have. From equation 1, we see that I over ED equals AG over GC. From equation 2, we see that AG over GC equals BF over FC. Since both of our side ratios are equal to that same middle ratio, AG over GC, they must be equal to each other. And finally, step 5. Our conclusion is reached. We have successfully proven that the ratio of I to ED is equal to the ratio of BF to FC. In the next slide, we will see how we can use the converse of this theorem to work in the opposite direction, identifying specific types of triangles. 3. Identifying triangle types. In our previous slides, we focused on using the Basic Proportionality Theorem to find ratios. But here, we are going to use the converse of BPT. Remember, while the standard BPT starts with parallel lines and gives us ratios, the converse works in reverse. It allows us to start with equal ratios to prove that a line is actually parallel to a side. Once we have established that parallelism, we can then use our knowledge of corresponding angles to determine if a triangle is isosceles. Let's look at this specific problem. We have a triangle PQR. A line, SD, intersects the side PQ at point S and the side PR at point T. We are given a specific condition. The ratio of PS to SQ is equal to the ratio of PT to TR. Our goal is to prove that if angle PQR is equal to angle PRQ, then the entire triangle PQR is an isosceles triangle. Let's break this down using step-by-step logic. First, we need to establish parallelism. We look at our given information. The ratio of PS over SQ equals the ratio of PT over TR. Because these two sides are divided proportionally, we can apply the converse of BPT. This tells us that the line SD must be parallel to the base QR. So, we can officially state that SD is parallel to QR. Second, now that we know these lines are parallel, we can use our parallel line properties. Specifically, we look at the corresponding angles. Because SD is parallel to QR, angle PSD must be equal to angle PQR, and similarly, angle PTS must be equal to angle PRQ. Third, let's relate these back to the angles of our triangle. The problem explicitly states that angle PQR is equal to angle PRQ. Since we just proved that angle PSD and angle PTS are equal to those very same angles, we can use substitution to conclude that angle PSD is equal to angle PTS. Fourth, let's look at the smaller triangle, PSD. We have just shown that the two base angles, angle PSD and angle PTS, are equal. According to the isosceles triangle theorem, if the base angles of a triangle are equal, then the sides opposite those angles must also be equal. Therefore, side PS is equal to side PT. Finally, let's reach our conclusion. We have established that the segments are proportional and the angles are equal. By following this logical chain, we can conclude that the larger triangle, PQR, is also an isosceles triangle, where side PQ is equal to side PR. Now that we have seen how to manipulate ratios and work with trapeziums, let's move on to our third and final application. Identifying triangle types. As we move to the next slide, keep this logical flow in our mind, as we will discuss some common pitfalls to avoid when solving these types of problems. Common mistakes to avoid. First, let's talk about ratio confusion. This is perhaps the most frequent mistake I see. When you are working with the Basic Proportionality Theorem, you must be very careful to distinguish between a part-to-part ratio and a part-to-whole ratio. For instance, do not confuse the ratio of AD over DB, which compares one segment to another segment, with the ratio of AD over AB, which compares a segment to the entire side. Before you write down your final answer, always pause and ask yourself, is my denominator just a piece of the side, or is it the entire length of the side? Second, be wary of assuming parallelism. When you are working with the converse of the theorem, as we saw in our discussion about triangle PQR, you cannot simply start by stating that line SD is parallel to line QR. That would be circular reasoning. You must first demonstrate that the segments are proportional, specifically, that PS over SQ equals PT over TR, and only then can you logically conclude that the lines are parallel. Finally, watch out for diagonal neglect when dealing with trapeziums. As we explored in the previous slide, the basic proportionality theorem is a property of triangles, not quadrilaterals. If you are presented with a trapezium, you cannot apply BPT directly to the four-sided shape. You must remember to use a construction step, specifically, drawing a diagonal, to split the trapezium into two triangles. Only once you have created those triangles can you validly apply the theorem. Now, before we wrap up our session with the final summary, I want to pause and discuss some common pitfalls. Even if you understand the theory, these subtle errors can lead to incorrect proofs. Keep these points in mind, and you will find much more success in your geometric proofs. Now, let's move to our final slide to review the key takeaways from today's lesson. Key takeaways. First, regarding extended ratios. Remember that the standard BPT gives us the ratio of segments, such as AD over DB equals AE over EC. However, as we derived in our second slide, you can easily convert this into a part-to-whole ratio, where AD over AB equals AE over AC. The mathematical trick to remember here is that you achieve this by taking the reciprocals of the segments and adding one to both sides. Second, when dealing with trapeziums. As we saw in our second major application, BPT cannot be applied directly to a four-sided trapezium. Instead, your strategy should be to draw a diagonal to split the figure into two separate triangles. By doing this, you can apply the theorem to both triangles and use a shared ratio to prove that the non-parallel sides are divided proportionally. Finally, regarding the converse application. Don't forget that the converse of BPT is your primary tool for establishing parallelism. If you can show that a line divides two sides proportionally, you have proven that the lines are parallel. Once you have established that parallelism, you can then use your knowledge of corresponding or alternate angles to prove that a triangle is isosceles, as we demonstrated in our final worked example. All right, we have reached the end of our tutorial. Before you move on to your practice problems, let's quickly recap the key takeaways from today's lesson to ensure you have a solid grasp of these applications. Keep these strategies in mind, and you'll find that even the most complex geometric proofs become much more manageable. Great job today!